Hey, happy Sunday, and this is PFG Live, and I'm Spencer Webb, and you're not. Welcome to the weekly podcast that asks too many questions and has none of the answers. Welcome aboard to folks in the Discord server. Welcome DBX and Josh, Unix Carbide, Tucker, Dale, Chris O, Carl Tauber, Sam, New York Machinist, Evils, Almost Machining, Jeff Williams, Jamie, and CJ Stevens. Welcome aboard. And over in the YouTube, we also have Carl Tauber, who says it's sunny and 34 degrees in the People's Republic of Rhode Island. Also in southern Manitoba, Josh is reporting winds are 330 at 4 knots, temperature minus 20 people. Dew point minus 29. Evils is reporting from somewhere that it's pretty comfortable in his room. Dale from northwest Snow Mexico says it's minus 18 C with a dew point of that's minus 1 F, and it's cloudy. Josh checks the audio and he says check. DBX in the Rockland County says that White Plains is winds 300 at 17, gusting to 27, visibility 10 miles, broken at 4,500 feet, temperature 00, dew point minus 11, pretty dry. Jamie says in Johannesburg, it's 20 degrees C, 88% humidity, and quite standard. Sam says the current furniture count is 2 out of 5 builds complete. Continue, please. And currently, the IKEA Helmer drawers are in process. New York Machinist still has his wallet. He says it's 25 degrees Fahrenheit, bright and sunny on the Cornell Hill in Ithaca, New York. Welcome. Tucker is here. He's also Iron Man. 29 degrees Fahrenheit. It feels like 11 in Buffalo, New York, where it is cloudy. Here in the Windham, New Hampshire, by the way, it is cloudy. Temperature 29, relative humidity 53%, winds out of the northwest at 12 miles an hour. Who else is checking in here? Jeff Dumas, welcome aboard, sir. He says, based on how upside down my garden shelter is, I think it might be a bit windy. I would tend to agree. Currently at Manchester, New Hampshire Airport, winds are 300 at 14, gusting 24 knots, visibility 10 miles. The sky is scattered clouds at 4,000, overcast 5,500, temperature minus 02, dew point minus 09, altimeter 2979. Remarks are unimportant. And I want to say welcome to the new subscribers. On YouTube currently, we briefly had a subscriber count that equaled the year. And that was 2 subscribers ago. So we're at 2027 for subscribers. Chris O checks in with sunny and 66 degrees Fahrenheit, 29% relative humidity in Los Angeles, California. Welcome. Paul Morley in Dallas, 39 Fahrenheit. Winds out of the north, dropping to 21 tonight. Welcome aboard, Paul. Pull up your blankies. Yeah, welcome. We had the whole holiday season. We were soaking in it for quite a while. And it was enjoyable. And we did a lot of stuff. And we did a lot of nothing. I took the opportunity, we're going to talk about this today. I took the opportunity to do a whole bunch of laser stuff. And the cool thing about the laser stuff is I could do it in my pajamas. No, don't read too much into that. The laser's in the basement, and I didn't have to, make too much of a mess. So it was pretty cool. What else happened? We had a new year. It's 2025. We're no longer my favorite aluminum, but I'll survive. Evil says the cool thing about laser stuff is that it's freaking lasers. And you are correct. It is freaking lasers. By the way, if you order a sticker pack from Kinetic Precision and you say the word freaking lasers, I'll make sure you get our special freaking laser stickers, one of which is right there. You can see our white freaking laser. And do we have the holographic one up there? I don't think we do. But that's courtesy of Sam, our artist. Oh, Dale put up the graphic. Oh, isn't that awesome? Paul Morley says he got great news on Christmas Day. He and his wife are going to be grandparents. Woohoo! Nice job, buddy. How'd that happen? Art that makes art says, pew, pew, pew. You are correct. Jeff says his second favorite aluminum is only 5,050 years away. We will all wait with you and be patient. Oh, Sam. Oh, there it is. I see it. There's the Holo one. There's our Holo laser shark right there on the sticker board. So once again, if you ask me really nice, I will send you one. When you guys got into the finger sandwiches in the green room, didn't you? I think you did. Anyway, we have some good stuff to share with you today. We had a lot of fun in the pre-show, and I'm sure we'll have a lot of discussions in the after-show. But part of my goal today, is to share with you a bunch of the lessons that I learned in this whole laser process. So we're going to talk a lot about lasers today. But first, the agent entered the main lobby of the building for the first time in 6 to 8 months. Finding the elevator and inserting the security card, proceeded directly down to the 6th sub-basement, never having been in the 6th sub-basement because this was the area where the cryptanalysts worked, and they were weird. Exiting the elevator, the agent noticed that all the rooms were labeled with room numbers in hexadecimal. Finding the correct room number was not difficult, but it was uncomfortable. There were 2 cryptanalysts staring at a screen. One short redhead who looks like he'd been there for 600 years, and one tall, lanky one with dark-rimmed glasses. As the agent walked in, they looked at each other and looked at the agent and said, "This isn't going to work." Up on the screen was several versions of the message that was retrieved from the vehicle, which said, "Check engine." The agent asked, "Well, what are you going to do? This was a message I got, and I need to know what it means." And they said, "Usually, it's just an indicator that there is a message, not that the message is understandable." At which point, the tall, lanky one handed the agent a small box. This small box had an electrical connector on one side, and that's it. The agent said, "What is this for?" The tall, lanky one said, "In the vehicle, there is a place to plug this box in, and this will enable us to retrieve the message." The agent took the box and left as quickly as possible. It did, in fact, work. The black box was plugged in, and a message, still encrypted, was downloaded. It was not understandable. The message said, "Air-fuel ratio error in cylinder 1." End of part 2. So, the continuing saga of the check engine light in my wife's Mercedes. And before we get into that, Quentin, welcome aboard. QD Smith says that the METAR from Echo Hotel Kilo Delta says that the winds are 220 at 21 knots at 190 variable 250, and a whole bunch. Oh, DZ, you got drizzle and rain, and what else? Few clouds at 1,500 feet. Cumulus clouds, temperature 10. It's warm, and cumulus clouds and drizzle. It sounds great. Who else is here? Okay, so second installment I purchased online a little black box called a Blue Driver, and you plug it into your ODB connector under your usually your driver's side dash, and there's a great app, and you use the app to talk to this little black box, and it sucks down all sorts of information, including why you have a check engine light. And the check engine light in Chandra's car said fuel air ratio error in cylinder 1. So I said, this is easy. We'll get some injector cleaner and we'll run it in the engine, and we'll unstick the injector. We'll get the thing clean, and we'll make it work. So ODB, like Wu-Tang Clan. I have no idea what that means, Unix, and I'm actually kind of glad. So before I headed off to the auto parts store, I said to Chandra, is it in warranty? And Chandra said, I'm not sure. So she calls, and sure enough, it's under warranty. And I'm like, I'm not doing anything. So we take the car over to the Mercedes dealer, and we drop it off. And we get back, and like the next day or so, maybe 2 days, she talks to Rob over at the dealership. And then she relays, so now we're playing the telephone game. She relays the story, and she says, yeah, Rob says it needs a head. And I'm like, hang on, say that again. She says it needs a head. And I'm like, I know what a head is in an engine. And I'm like, are you sure he didn't say head gasket? And she said, I don't know, he might have said head gasket. I'm like, no problem. I'm going to call Rob, and I'm going to find out what he's got to say, and I'll understand the engine stuff, and we'll be good. So I call Rob up. Rob's a super cool guy, knows his stuff. We really like this dealership, by the way. And he says, yeah, the engine needs a head. I'm like, what? And he says, yep. He says, don't panic. He says there were some engines that left Mercedes that had a problem, and the head had to be redesigned. Your engine is one of them. And it's going to take a couple of weeks, and we're going to get a whole new part number, newly redesigned head, and it's going to fix your problem. All no cost. So thankfully we do have a third car, so we're okay. But that's the story. The relatively young, not too many miles, Mercedes is back at the dealer getting a new head on the engine. That's the source of the check engine light. And I just wanted to follow up, let you know, just so we didn't leave that one hanging. We'll report when it's back, and we'll close that story up. So there you go. I am aware of the Wu-Tang Clan. I did not know what ODB meant with respect to Wu-Tang Clan, but I am open to learning. I have mentioned that I'm working on a project, and the project has a lot to teach. But it's an RF box for a client. It's passive. For you RF guys, it's basically a signal splitter, a pretty fancy signal splitter. And it has a couple of pieces, a couple of chunks in it. One of the chunks is called a quadrature hybrid, and one of the chunks is called a Wilkinson divider. Now, we can get into this really deep, but it's not worth it, trust me. But the way this thing is made is that these things are fabricated in what we call a strip line. So there's a ground plane and a ground plane, okay? And down the center of between those two ground planes is the transmission line, and that structure is called strip line. And these things are made out of brass, and they go down the center line. And so I had these patterns that I had to get made. Before coming up with the patterns, there was a whole other history of this project of how to figure out what to do, which I'm not going to bore you with. But when I started designing the elements, I used software, electromagnetic modeling software, and in that software, not only did it simulate the behavior and the performance of these components, but it gave me the opportunity to optimize the performance of the parts. So, for example, we'll use as an example the Wilkinson divider because it's a little simpler, and I'm going to show you one. Okay, so there's the Wilkinson divider, and if you're on audio only, I'm sorry, but you'll have to just get the video version. So it looks like an input at the bottom, right? And it splits down two paths, and the two paths are independent. And at the end of the two paths, they have two outputs. And don't worry about the rest of the details. But these two paths form transmission lines, and those transmission lines have to be a certain characteristic impedance. That's controlled by the width of the lines, and the length of the lines control the frequency of operation, which is also part of the specification. So you go into this electromagnetic modeling software and you draw this thing up and you put it in its environment between these two plates, and you say, I want perfect division of my signal. I want perfect matching for a 50 ohm system. And here's the knobs you get to turn. You get to turn this width. You get to turn, the spacing. These are all the things you can change, Mr. Software. Now, when it runs a simulation, it will generate a score as how close you're getting with respect to all of the targets you gave it. You can give it one target, or you can give it 50 targets, and it will come up with a score for each of those targets, and it will add them all up to one number, and that number wants to be 0. 0 means you meet all requirements. If that number is higher than 0, that's the error. And you keep turning knobs to drive that number down. And that process is called optimization. And everything, anything that gets designed with computers these days, you have usually an optimizer. Even in Fusion 360 for mechanical design, we have the ability to run simulations and run an optimizer and say, I want you to make this as light as possible, but be this strong. That's optimization. So optimization is pretty simple when you have one variable. So if you're grinding and you're grinding a part and you say, I need this part to be exactly 3 inches long, it's very simple. You measure it, and if it's more than 3 inches, you subtract 3 inches from that, and that's your error number, and you keep on grinding until you get to it. So that's physically implementing optimization. But what if you have, you have a computer simulation, but you have 5 variables. You have 5 knobs you can turn, and you're trying to get the error down. Hopefully, if it is, if everything's governed by equations, you can kind of look, you could do it mathematically to find the optimum, but it could be arbitrarily complicated, and it can be also what we call chaotic, meaning it's really complicated. So you kind of heave it over to the optimizer, and literally what the optimizer can do is change one thing and see if it gets better or worse. Change the next thing, see if it gets better or worse. Change the next thing, see if it gets better or worse. And that optimization process has many flavors. There's many ways to approach this. There's the simple Newton method, particle swarm optimization, genetic algorithms. I mean, it is nuts. Wes says, what if there's a glitch in the matrix? Dude, there is always a glitch in the matrix. So imagine, if you will, that you have, let's say, a solution space, right? Let's just imagine a two-dimensional, surface, or a surface that has peaks and valleys, like this, like a landscape, okay? And your job is to find the lowest point in the landscape. Yeah, Dale, it's exactly right. He says it's like when you're getting eyeglasses at the optometrist. Remember, optometrist turns the thing and says, "Which is better, A or B?" Now, which is better, A or B? Okay, except now make it 7 variables, and you have this solution space. So you're looking for the lowest point on the landscape. So if I sent you out of my house and I said, go find the lowest spot, you'd have some questions. You'd say, how much of this area do you want me to investigate? That's the first question. Second question you might say is, how accurate do you want me to be to measure the height of the landscape before I come up with a number? Evil says the lowest point is clearly your well. Okay, so my well, let's just say my well is 200 feet deep, which, by the way, it's not quite that, but it's almost that. So if I sent you out to find the lowest spot, you might find a nice low spot down the hill, and you might stop and say, I found the lowest spot. Because you looked around, everything else looked higher, but you didn't look down the well, did you? So another strategy could be, I'm going to look everywhere, every square centimeter. I'm going to check the height. And you would find my well in 200 years. Okay? So that's the trade-off, is how do you do this? So I've just explained to you a very big chunk of what I've done for the last 25 years in antenna design or RF design, which is you're looking for you're looking for this optimum for your design and working with the computer, and it's a very complicated thing. So when we design stuff like this is exactly what we go through, right? And we end up with this design. Now we have to go make this design. Okay, and Dale says, you know that you check the well because you know to check the well. In other words, you have some knowledge about what's the best places to look. Okay, we have a name for that. That's called an expert system. Okay, so if you go to a system that's optimized for example, making filters, enter the laser. Then it could say, well, I know about filters, and this is the first place I'm going to look for your optimum, and that would be an expert system. So here's another example. This is from literally 30 years ago. This is an antenna that was designed for a customer. I'm going to turn it around because I don't think it's important that you know who the customer is. And this is an etched piece of brass, okay? And it has some fold-over little etched lines where you can fold it. It actually gets 2 folds. And when you're all done, you have a little thing that a radome fits over. And in this case, it's called a railroad antenna. And you can look it up if you want to. I think this is for 900 megahertz. And it was etched brass, and then it was plated in tin. Okay, and this was a successful design for a client. So along comes this project, the current project that I'm talking about, which is going slower than my client wished it was going, but we're getting there. And naturally, I come up with this design, and I said, oh, I'm going to go get this etched. So what did I do? I went to the same company I went to, 20 years ago or 25, whatever. And I'm not going to tell you their name either, but it's a high-tech etching company in the area, and they did that job for me. So I went back to them, and I said, hey, here's a drawing. This is what I need. It's 25 thousandths thick brass. Please quote me. And I get a phone call. I emailed with the engineer, but then I get a phone call. And the phone call says, hey, I'm in the business side of things, and I'm just calling to see, what's the potential of this product. Like we were told by management that we're not going to take every project. We need to understand the potential of this project. And I'm like, okay, you do know that I've worked with you guys over the last 3 decades. That didn't seem to matter. So I said, look, this is a project for a government adjacent project, and we have to get this thing done, and I need 20 of these things, and that's it. And there may be more down the line, there may not. But this is an engineering project. And I was imagining in the time that this was going to cost, I don't know, $1,200, $1,500, $2,000. That's kind of where I figured this was going to land. So they said, okay, well, I think we understand, and yes, we will take care of you, and we will get you a quote. So this business person unlocked the ability of the engineering department to give me a quote. And the quote comes back. Now, keep in mind, imagine about 10 of these and 10 of these, okay? 2 little squiggly things. 10 of these and 10 of these. And the quote comes back, $7,000. So 2 words immediately spring to mind. And I'm not going to explain which 2 words they are, but they were not in the affirmative. And yes, Dale almost has it perfectly correct. And I'm like, really? $7,000? So Dale, I'm flaming about this on our Discord server. And Dale says to me, you could make this. He's sorry. He says, you could make this. You have a laser. And I'm like, yeah, I know, but I'm trying to I already outsourced the housing, by the way, to excellent effect, to one of our partners in crime. Is he here? No, I won't. I don't have permission to talk about it. So, and the housings got done, and I wanted to outsource this so I can get on to the other stuff. But Dale's like, no, you could make this. I'm like, it's 25 thousandths thick. I've never cut anything in my laser. I've never cut anything. I've engraved. I haven't cut. So, okay, if you're a machinist type, and if you're listening to this, there's a high probability that you are. I want you to imagine that your only tool is 1/8 inch diameter end mill that's 2 inches long. Okay, and I want you to cut out a piece of 1/2 inch plate. Okay, what are you going to do? 1/8 inch tool, 2 inches long. That's how much it's sticking out. 1/8 inch all the way, and you have to cut through a 1/2 inch of plate. Can you do it? Yes. Is it the right tool? No. There's a whole list of tools you'd rather have than that tool. But this is what I was faced with. I had a 30-watt fiber laser, and I had 25 thousandths of brass to cut. So I started doing experiments, and I started seeing what I can do. And if you looked at our thumbnail for today's video, you can see a couple of interesting features in that photo. By the way, I will share with you that one of our parts is getting cut right now. And here's a picture of it. I'll explain what you're seeing in a minute. But if you're on video, you're seeing a live feed from my laser down in the basement. And there's a couple of things that are obvious. One of them is this thing is starting to pop out of the sheet, which is actually cool. The second thing is there's this work holding frame that I had to design. That took a while to pop into my head. A couple of weeks ago, we were talking about doing this, and I had it in my head that we were going to glue a piece of brass to a piece of aluminum and laser it while it was attached to the aluminum. those experiments were difficult and they didn't yield a good part for various reasons. The camera mount is super high tech, Dale, but I'm not going to show that today. So eventually we ended up, a couple of people said, well, why don't you hold it like they hold it when they laser cut on the big machines, or they a water jet cut. So you hold a big sheet either on the honeycomb or on the points. So basically there's nothing but air behind it. So what I did is and this was again talking to others, I talked to Unix Carbide. He's a big fan of this 80-20 extrusion material, which I got a piece of right here. So here's, you guys have heard of these extrusions. Now 80-20 is just one brand, but there's bunches of them now that make these. And he said, well, you could use that stuff and make build whatever you need. So I designed and built a frame, a square frame, to hold this sheet of brass. Okay. And this is what the brass, I settled on a 6x6 inch piece of brass, and I built a frame to support a 6x6 inch piece of brass. So there's air under it. And then I designed these hold down clamps, which were able to just clamp down the edges. And of course, the hold down clamps were 3D printed. And then the hardware is the same hardware that goes with the extrusions that's in the McMaster car catalog. It's these little slide-in nuts, and it's these screws. Yes. 80-20, Quentin, is I think that's where the name of the company came from, but now the company name is 80-20. This is 20 by 20 millimeters. Okay. So I made and this is going to bother somebody. I'm looking at you, evils. I made my 6x6 inch frame out of 20 millimeter extrusion. And wait till I tell you the laser cutting speed in furlongs per fortnight. That's coming. Don't worry. So then we started doing experiments with, okay, how does this thing start cutting? So I'm going to show you an early experiment. And the early experiment was, eventually got to some pretty decent results. And one of the things that I ended up doing was cutting not one line around the part to expect it to cut, but to start cutting multiple lines to create a bigger trough around the cut, because I had to do many, many cuts. And the laser, if it got too deep, the laser would be obscured as it's trying to get to the bottom of this cut. Remember, it's an underpowered laser. It's not going to pierce. So we start making many cuts. So I ended up going to 5 total paths around the shape, offset by various amounts. And I did, here's some remnants of some tests. You see it says cleaning pass test, and it says 2 4mm offsets. It ended up that I would do a path, and then I would step over 2/1000ths of an inch, and I would do another path, and I would step over 2/1000ths of an inch, and I would do another path. And that was done for 5 total paths. That started working nicely. It took, ultimately, my rule of thumb was, for my power level, I was cutting a 0.5 of an inch per pass. So I would do a loop, a loop, a loop, a loop, and a loop, and then I would do it again, and I was expecting to cut down 0.5 each time. And that started working pretty nicely. Then I noticed another problem. Okay, if you look at the back of the sheet, and this was a hidden advantage of this frame. And in the machine, I have pins on this. I have a tooling plate at the bottom of the laser bed, and the tooling plate has holes, unthreaded holes, and I have these pins in the tooling plate that I made. So I would have 2 pins on one side, 1 pin, so 2 pins in to the left of X and 1 pin to the top of Y, so I could register my frame, which also means I could take my frame out, look at the bottom of my sheet, and put my frame back in. I cannot tell you how useful that was. Yeah, Greenwood AG says time to step up to a more powerful laser. We'll talk about that in a minute. So if you look at the back of the sheet, you see I'm starting to win here, right? I'm starting to cut all the way through the sheet. This was wonderful. On the front of this sheet, you'll see some notations. One says 30, one says 40, one says 45. That's the total number of passes. And honestly, even at the 30, it was working. You could see I'm pushing out the part. But if you try to get this part out of the sheet, it's just not quite all coming out, and it's very hard to get out without damage. So this led to the next idea, which was, and I'm just pulling parts out of the out of here. Here's a good. So what we're going to do now is we're going to do additional cuts in the swarf, in the unwanted, not swarf, but in the cutoff material, and we're going to weaken the material around the part. And if you look at our live shot here of our part, you'll see that when the parts get lasered and material gets removed from the top, the parts want to curl up. So cutting these weakening cuts, everything starts wanting to fold out, and it almost self-releases from the cut. And that was sort of another breakthrough, if you'll pardon the pun, as to how to make this thing happen. So, long story short, you can see multiple sheets of success here, where we were cutting out parts, and you see the remnants of the release cuts on these parts, but the parts have been removed and the parts are stacked over in the good pile. And one of Josh said these breakouts, we can make earrings out of them and sell them. So that might be a secondary business. But it started working beautifully, and I am cranking out. These are actually these are pretty good parts from the process. Not perfect, so these are just show and tell parts. These aren't usable parts, but we're cranking these out, no problem. I will have made all the parts I need between the time I got the $7,000 quote and the holiday started, and now I've made all my parts. And I have not responded to the $7,000 quote yet. Guess what tomorrow is? Tomorrow's Monday. And guess what I'm going to start doing? I'm going to start replying to the quotes. Now, after I got the $7,000 quote, I immediately put out 6 RFQs to 6 other companies for this work. And a company on the West Coast, who one day I will give them a shout out, but not at this moment. They got back to me with a quote and a layout. They showed my parts in a layout, and they wanted to know where I wanted the tabs, and they were ready to go. And the quote was about $2,000. Okay. If I did not own the fiber laser downstairs, and if I did not have, if you'll pardon the expression, a bug up my butt, I probably would have hired those guys to do the parts immediately. Notice that I did not say that about the $7,000 quote. So, but it forced me to use what I had and get the job done. Another part of the process development, if you look, if you Dale gets all the credit for putting the bug up my butt. Don't read too much into that. If you look at the thumbnail, you'll also see a little, I might be able to zoom in on here. Let's see. There we go. I made a little, it almost looks like a calibration target, but I started experimenting with one of the parameters, which is the laser focus. So the way the laser works in this machine is that it gets generated and it travels through the machine, bouncing off of mirrors, and the laser is about 1 inch in diameter. It's a big spot. Only at the last minute in the head of the laser, which you can see right there, right in that black tube. Yeah, Greenwood, exactly correct. The 7,000 was a go away quote. No problem. Hey, I'm in business. I get it. But they'll get a response from me. Don't worry. So right in that tube, in fact, you might be able to catch a glimpse of a mirror and a lens. So there's the lens. That's when the laser goes through its final optic and it gets focused down to, we're figuring, a 1 to 2,000th of an inch diameter. That's doing the cutting. But what that means is that focal point is critical. So I started doing these experiments with what should the focus be set to in the software. It turns out that I read somewhere that it did not want to be at the surface. It wanted to be subsurface. The focal point wanted to be subsurface. So I started doing these experiments. Now, this was not the first test pattern I made, but this was the last test pattern I made because it was really effective. Number one, I labeled it. Okay. So yeah, I didn't have to wonder which test was this. And the second thing was I did 5 data points. Now, remember we were talking about, I'm looking for one of my examples here. Here it is. Remember we were talking about when you do these optimizations, you try a bunch of stuff and you figure out which is the best one, and then you set the parameter to that one, and now you go work on another parameter. So in the focus point, in this case, I was testing minus 0.02, 4, 6, 8, and 100, right? So that's what you're seeing on your screen, and it turned out after getting this plate and doing microscopic examination, I figured out which was the best one. It turns out it was minus 0.04 was the best focal point. So now I had a starting point. Here's another. This was the earlier one. I don't have a photo of it, but there it is right in front of you. It says focus minus 0.02 to 0.1. Oh, this is the one that went to 100. And you'll notice there's only 3 rings visible because the focus that was too close and the focus that was too far didn't cut the brass. So then I took the best one of that and I went to the other strategy, which you see right there. Yeah, you caught me, Robin. Yeah, this one is 2, 3, 4, 5, 6, correct. And this one was the 20, 40, 60, 80, 100, right there. Right there. Ironic that I'm waiting for it to focus on the focus. So what were the number of parameters we had to optimize? So there was the focus, there was the speed of the laser, which actually had a surprise in it. There was the power of the laser, and then there was something that Epilogue calls frequency. I love you, Epilogue. It's not frequency. It's kind of duty cycle. Okay, we have to talk, but anyway. So power, we knew we wanted the power set to 11. That was no issue. It was like full power. Okay, frequency. from my reading, the lower frequency had the most power per pulse, and that was best for the cutting. So we set that to 1%. Then there was the travel speed. Now, travel speed went from 1% to 100%. It turns out it's, I think, 3 feet per second, or 1 meter per second was the maximum speed. Don't hold me to that. And you would think that the slowest speed is what you want. It turns out, from experimenting, the slowest speed is not what you want, because what happens is it gets very hot in the vicinity of the cutting, and that causes warpage, and that was causing a problem. So by using a higher speed but more passes, we got a better result. We found that out from experimentation. It's the only way we're going to learn it. So that, and of course, that was the another parameter is number of cycles. Okay. So 5% travel speed was nice. It was slow enough to deliver a punch, but fast enough not to warp the material. So here's the recipe, and think of all these pieces that had to get sorted out. It's 1 pass per half thousandth. So I'm using 50 passes for 25 thousandths thickness. So 50 passes, 100% power, 5% travel speed, which of course translates to a real number to be determined. 1% quote frequency, and then you add in the multiple paths, starting with the path near the part and marching your way out to make a place for the laser to go. That went from 5 paths. I have reduced it to 4 paths, and without giving up any quality, but 4 to 5. What else? And then the relief cuts are not multiple paths. They follow the same cutting recipe, but they were only it's only 1 path. Okay, and they do their job quite nicely, as you can see from the side. We have a question from Evils. He says, aren't these parameters independent? Are these parameters independent? For the most part, the parameters that we just talked about are, well, you could argue that the number of passes and the travel speed are interdependent. So, except for the quality they yield. Both will cut, but one of them will cause a warp that ends up being a problem later. So, Wes says, can you put a fan on it to keep it cooler and blow away the cuttings? So the reality is, if you look to the right of that black tube, you'll see there's a little air tube attached to it. That tube is receiving 10 psi, and that is blowing air down at the part. And that keeps the ejecta from the brass from getting to the optics, but it also blows on the part, which tends to keep it cool. So you are thinking correctly, sir. So that is already happening. The other thing that's happening that's not obvious from this video is that there is a big air filter sucker vacuum cleaner that's sucking air out of the laser into a HEPA filter, because it's not getting exhausted outside. And that also ensures airflow through the whole system. So this whole system is under airflow right now. Okay, so Robin asks a great question. What happens to the focus with all the part deflection? It gets screwed up. Now, if the part deflects, which causes a problem with focus, it doesn't matter anymore because the part deflected. So just experientially, there's actually an answer for that. What I do is I have 3 phases of cutting the part. Phase number 1 is I do a raster engraving of the part number or the revision number. If you look at this picture at the lower third, you'll see it says P5. That's the revision number of this cut. Okay. The second phase of cutting is the part cutout. Okay, it's the one that creates the shape of the part. So the heavy line, the heavy black line that you see, is the second phase. Only after the second phase is done does the weakening cuts start. So the probability is that there's no or low deflection during the important cutout. However, it doesn't cut all the way through. And then when you come back in with the weakening cuts, the stresses go, and it lets go. But at that point, your precision has been kinetically induced. Do you see what I did there? From the first cut. So 3 phases. Number 1, put your nomenclature on the part. Number 2, do your utmost to cut out the part. And number 3, come in with the weakening cuts. And that's how I handle that. And it works great. Now this looks horrible. This looks like, oh my gosh, this is a mess. And the fact is, it's not a mess. If you're on our Discord server, I published a little 1-minute video of me removing the part from this, and it comes out magnificent. And if you're really careful, it comes out dead flat. So it works. It looks crazy, but it works. What's the wall? The wall geometry is excellent. It looks very, very straight. I can get you a photo micrograph, but you'll just have to take my word for it that at the moment that the wall here is very flat. And again, that's because it's the first thing you cut in any of these passes is that wall, and then you step away from the wall. Step away from the wall, please. So it comes out great. It comes out fantastic. Wes says, could you tape and super glue them down? Super good question. So the tape idea, there's too much force. Okay, there's a lot of force. I did super glue parts down, and I could probably go back to super gluing. So in this optimization, I have to bring you back to optimization. There's what we call local minima. So I didn't get to use that term before. But when Evils goes walking around my property and he gets to the bottom of the hill and he says, I found the lowest spot, but he didn't find the well, we say that he found a local minima. So we have found a local minima. In other words, am I making good parts? Answer, yes. Is there a better solution? Answer, possibly. Do I care? No, because if you add into the optimization the calendar, I am happy I found this particular minima. So it's not that I can't do it better. So one of the ways of doing it better, I think, is going back and revisiting the super glue down to a substrate along with all the other lessons we learned. Because one of the hypotheses was that gluing it to the aluminum plate was thermally going to be a problem. Carl pointed out that the thermal diffusivity of aluminum is very high, and that is essentially was going to cool off the material. But I think we've disproved that was our limiting factor before. And now part of me wants to go back and investigate it again, in which case you would super glue the part down to a nice flat substrate, you do your cut, and then you'd heave it into a bucket of acetone, or you'd use heat release. which I have successfully done in milling very thin parts, is heating it up to 400 degrees and the CA releases. By the way, if you do that, please use extreme caution because at 400 degrees, cyanoacrylate turns into a white smoke and beautifully releases your part. And I don't know what that white smoke is, and I do not want to know. And then your part gets tossed into acetone and it gets cleaned up. Robin asks, doesn't the focal cone end up generating a taper on the part edge? I am almost certain that we can find a taper if we look hard enough, but it's not worth, it's not that critical for me right now. But it's a good question. If I can grab some pictures under the microscope, Robin, I will send them to you, and we can take a look to see how good it is. For my purposes, which is, if you remember, we're making an RF device here, I don't care. so we can look a little closer and find out. Yeah, and the other thing to remember is it's almost exactly like an end mill marching down, a relieved end mill marching down, or even an end mill with some taper marching down. If you ignore the deflection, because of course it's a laser beam, it doesn't have deflection per se, it's only going to be cutting at that focal point. So it actually does march down, and the wall ends up being pretty straight. But I'll investigate it and report back. So I think I answered your question, Wes, about a super glue. It was an initial thought, and we actually stepped away from it. Okay, this is another experiment we did. Robin asks, if focus matters, are you adjusting it for each pass or after X number of passes? Okay, I tried it both ways. And I had early success with adjusting the focus as you went down. And if I had my druthers, I would do that now. The problem, the stumbling block for doing that is, wait for it, software. So I would have to generate it. It's easier to show you than to try to describe it. But in the Epilogue software, which is a printer driver, okay? So when you design the stuff in Adobe Illustrator, oh, by the way, part of this whole process forced me to get into Adobe Illustrator and understand Adobe Illustrator. And I went from 1% expertise to 20% expertise. That's pretty good. So thank you very much for the $7,000 quote. It made me learn something. I appreciate it. So you generate your artwork in Adobe Illustrator. You color code it so that you have 3 different colors, and then you go and you say print, and then it goes into the printer driver, and the printer driver is the Epilogue software, and it says, oh, how do you want to treat the red stuff? How do you want to treat the blue stuff? How do you want to treat the black stuff? If I wanted to go down and, for example, and I did this, by the way, create 3 different levels or 5 different levels, I would have to have 5 different pairs. So I'd have to have 10 recipes in this thing. It sort of was a trade-off between how much time do I want to spend on the setup. So in my case, I didn't do it. I decided the view wasn't worth the climb, and I am getting good parts. So yeah, if I could have written the software, or if I could have had software that allowed me to specify that, and that wouldn't be so hard to do, Epilogue, I'm looking at you, I would have done that. And Unix Carbide says, doing the same thing, learning with Inkscape right now. Yeah, it's amazing what you could learn when you get forced into it. But Illustrator went from just a mysterious mess to okay, at least I understand how to use it. And like I said, I'm probably at about 20%. What's the bottom line? The bottom line is downstairs we're cranking out parts that are totally usable. Now the next step for these parts is to take off the burrs so they'll get lightly sanded on the Labzetti plate. The edges, these edges are probably going to get polished a little bit with my new NSK rotary tool. I'm very excited about. And I could probably show you a picture of it. I literally opened it up just before we came upstairs to for the live. And that's one of the reasons I bought it. So we're probably going to kiss that. Evil says, you bought the NSK with the $7,000 you saved. Yes, I did, sir. Because to get this project done, other than raw materials, other than brass, okay, I didn't buy any new tools. So yes, the NSK was bought with my savings. Greenwood says, is water jet cutting a possible process, or does it introduce too many new unknowns for thin materials? The answer is I don't know. If a water jet company came to me and said, we could do that and we could, achieve the same thing and it'll be cost effective, I'd be all ears. I'd be very interested. I also could have done etching. Like, etching doesn't scare me. It could have been another process. The other thing is, you may recall that I said I was doing this in my pajamas. This was a dry process. No chemicals. Okay. It just takes a long time. Unix Carbide says, mod a 3D printer with a carbide chisel bit. Possible. I do have a friend, more importantly, at the makerspace, we have a water jet. It's not a Wazer. It's I don't remember, but Wazer is more hobby-ish, and this is a step up from that, and I don't remember the name of it. Again, wet process, lots of consumables, learn a new machine, so I didn't do it. It's possible. Dale says it's not great on thin materials. I found anything under 1/8 inch warping is a problem. I'm stunned at how little warp, how little. I mean, you look at the picture of this thing doing its thing, and you'd say, "Oh my God, that's going to come out of that looking like a pretzel." Yet, the whole point of it is it comes out flat, which is pretty cool. Paul says, you mean waster of time? Yeah. Okay. So Wes says, we're going a little over, folks. There's a couple of points we have to finish up with, and then we'll wrap it. Art says, Art that makes art, which is Wes, says, with a CO2 laser, you could have done these also. You could paint the brass, laser off where you want it cut, and then etch it. Yes, yes, yes. In fact, I just watched a video literally last night of a guy doing PC boards using that process, and I think it's brilliant. Okay, so let's talk about lasers and sheet metal. So I have a fiber laser. I hate the name fiber laser because it tells you absolutely zippo. You know it's a laser. The next thing you need to know is the wavelength. So a fiber laser, in my case, is a 1 micron wavelength laser. It will cut metal. Okay? Rod, 842, asking to speak. We'll give you a shot, bud. Hang on. No, you're unasked to speak. Okay, so 1 micron laser cuts metal, no problem. Why? Because the wavelength is similar to the size of the molecules. No problem. 10 micron wavelength is the same as CO2 laser. All right. CO2 laser will cut acrylic. Why? Because acrylic molecules, it's actually a polymer, are big, and so is the wavelength of a CO2 laser. If you take a CO2 laser and you point it at this piece of brass, you get a shiny piece of brass. It won't cut it. If you take my fiber laser, this is the funniest thing. I know I've told this story before, but if you take my fiber laser as it's etching metal and it hits a piece of blue painter's tape, it stops. Like, it does nothing to the blue painter's tape. It's amazing. The fact that the laser, do I have an example here? I don't. The fact that the laser is used to mark PFG stones is a happy accident, which I'm not going to get into, but it's the reason I bought the laser is to mark PFG stones, which it shouldn't do, but it does. So that's why I own that laser. So up until this project, I never did a vector cut with the laser. It was a raster, like a printer. And this project forced me to do vector cuts and understand how to set them up and execute them with the laser. Thank you for your $7,000 quote. Dale says, from my experience, most high-power laser can't go low enough. My local shop won't touch anything less than 16-gauge steel as they can't get the power level low enough. I did look at... Oh, take care, Robin. Hey, thanks for checking in, man. Even for a flyby, you were a contributor.
I am not an expert.
So, you're awesome, Robin. I called I sent, went to the website for Send Cut Send, and they won't touch anything under 40 thousandths of an inch, I think, was their limit. So I did look at other sources. That's the story. So much was learned. Just pounding away at the laser over from before Christmas to after New Year's was fantastic. Didn't take me away from home. Took a long time. This part, I hope you're sitting down, okay? I'm going to get you, Carl. This part takes 6 hours. Now, I know what you're thinking. You're thinking, that's ridiculous. I don't know. My laser sat around for a lot of 6 hours in a row before we came to this project. And I'm almost done. So 30 watts, it takes a long time. Okay, let's see if I can get you. Carl Tauber from Rhode Island. Hello, you're on the air.
Just a quickie. You're off by a factor of 10,000 on the size of the molecules. The reason the infrared works well, or the 1 micron works well, is because the skin effect confines the heated zone shallow enough that you can actually heat stuff up and vaporize it. And if you go to 10 microns, which is CO2, you basically need way more horsepower to get the stuff hot.
Okay.
And so,
but why? Okay, so then why does the? Oh, you said the magic word, skin effect. So why will the fiber laser, the 1 micron laser, not touch, for example, acrylic?
Because the acrylic is transparent at that wavelength.
Okay, how about but also blue painter's tape?
Same deal.
Okay.
And the reason the CO2 works well is because it's absorbed by almost all organic materials.
Okay.
So essentially what happens is you absorb the energy in a shallow depth so that you can burn stuff away.
So you're saying that I gave an oversimplification without basis on physical fact. Is that what you're saying,
a little
sir?
Bit.
You can say, dude, it's okay. But
No, I just thought it would be of interest, given this crew has,
yeah,
is not single-minded, so to speak.
the nerd is strong in this crew, is what you're saying.
Yes, sir.
Thank you very much. At the very least, we have a way to remember it, right? And Carl, the thing that I need to know, and I haven't done enough research, is that there are diode lasers out there that suffer from the same problem of not specifying the actual wavelength. And some of these X-tool lasers are in that category.
Understood. And one of the problems that is always a concern with diodes is that the beam quality is not as good as it is from a fiber.
Yep.
And that means that the focal spot is going to be larger, so that you can't necessarily confine the energy into a narrow enough kerf in order to make cutting effective. Diodes are used all the time for heat treating and welding, because they provide a lot of power, and you don't need a very tiny spot size.
And they're cheap.
And they are cheap. And in terms of dollars per power, you can't beat a diode.
Okay. Carl, thank you so much.
Very good.
I'll catch you later. All right. So thank you, Carl. Carl's down in Rhode Island, the People's Republic of Rhode Island. Quentin says, especially with the combined lasers, my 40-watt Creality Falcon laser has 8 5-watt laser diodes. There you go. I think we've done it. We could probably talk about this stuff for another hour, but we've hit the we've gone past our normal time. I hope you enjoyed some of this material. More to come. Very excited about finishing this project. When we get to the end, if my client says we could talk about it, we'll talk more about it. But there you go. So from Windham, New Hampshire, home of PFG Stones, which if you need some flat stuff, head over to pfgstones.com or just go to pfg.gg and you'll find it. And you guys managed to clean me out. We have 4-inch stones getting ready to grind downstairs. Probably be a couple of days before they're out. And then 6-inch stones are right behind it. If you have any questions, don't hesitate to drop me an email. If you're on our Discord server, we're going to be in the after party roundtable for a while. This will be out as an audio podcast, and I wish everybody an awesome rest of your weekend, and we'll see you next week. Get flat, stay flat.